So I'd like to everybody introduce you to Dr. Emmanuel Fonseca. He's a WVU radio astronomer. Let me just read a little bit about his bio for everybody to kind of set the context here. So Dr. Fonseca, his research interests include radio pulsars and fast radio bursts, largely interested in relativistic dynamics of pulsars and orbital systems, as well as applications of fast radio bursts for cosmology. Prior to joining WVU in late 2021, I worked as a postdoc at McGill University of Montreal, Quebec, Canada, from 2016 till 2021. He attended the University of British Columbia, where he obtained his PhD in astronomy. And before going to Canada, he obtained dual bachelorette degrees in physics and astronomy at the Pennsylvania State University. Born and raised in Malvern, Massachusetts, and your parents came from Bogota, Colombia. So here's some good stuff, because I'm a mission guy, so I like this. So since 2016, Dr. Fonseca helped construct software and hardware for the Canadian Hydrogen Intensity Mapping Experiment, CHIME. We always hear that. Or see the acronym, never really know what it stands for. CHIME telescope, as well as two of its instruments, and using for pulsar observations and FRB. Currently helps maintain both instruments for CHIME, as well as supervises and co-leads science projects using the instrument. Also uses the 100-meter here at Grain Bank, the former 305-meter Arecibo Observatory as well, and the very large array. Since 2011, has been a longtime member of the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, and he works with NanoGrav observing and timing groups to characterize millisecond pulsars. And so please, let's welcome Dr.
Thank you, folks. Thank you so much, Marcus, and thank you all. Really, I'm sure you folks feel, I'm always really grateful to be in this location, this space. Fairbanks really is a wonderful place to be. So I'm very, very happy to talk about something that I actually don't, for the record, as Marcus said, I don't actually study the 21 centimeter line for research. Obviously, as a radio astronomer, I'm quite intimated with its history and its details, and I hope to share some of those details and histories, things you may know, things you may not know, so that we can all take something new from this talk for sure. But yeah, please don't hesitate to ask any questions. Let me know. Feel free to stop me whenever. Very happy to chat. So, like I said, and as the title slide indicates, I'm going to go through just several kind of big picture things as to what the 20 centimeter line is from a historical point of view, from a physical point of view, from the applications of 21 centimeter and why it is so prominent in radio astronomy. And I'll just very, very briefly summarize all that stuff. So first and foremost, I'll go through essentially what is a historical introduction, right? So I think as you folks are aware, as folks who are passionate about radio astronomy and or radio instrumentation in general, the history of physics is always something I like to engage with, and is really, really interesting, right? Because it turns out that a lot of what we do today is essentially the consequence of what you could arguably characterize as happy accidents, just folks who are genuinely curious and interested in making sense of things. For example, what we now call radiation, which folks like Sir Isaac Newton, Sir Thomas Young, etc., back in the day. Back then, they didn't know what light was. They were trying to make sense of it, and in the process of trying to experiment with this phenomenon, found that, oh, white light can be decomposed into colors if you shine it through a medium that's not air or not vacuous, like a prism, for example. Obviously, this is, led to the inspiration of some amazing album cover art for sure. But the idea here is that it was through this sort of inspiration that we, as scientists and physicists, gradually came to understand what we now call radiation, and radiation being not just what we can perceive with our eyes, but something that is part of those things that we can see with our eyes. The optical or visible light is in fact part of this overall electromagnetic spectrum. Right, the radio is on one end, X-ray and gamma ray radiation on the other. And the idea here is that it was through this experimentation, these happy accidents, as I refer to them informally, that we were able to piece together the existence of radiation in different ways, at different scales. And it was through the ways in which those pieces of radiation or those parts of the spectrum interacted with matter, other things that we could perceive, that we were able to detect their presence. And I, just for the record, I denote the dates, the rough dates or periods of time when the parts of the spectrum were basically discovered. Again, visible light, for sure, we've known of for essentially human history, even if we didn't really realize it. But the rest of the spectrum, as you can see, they weren't really discovered formally until the 19th, 20th centuries and so on. But again, it was through that discovery that all sorts of other things in the history of physics were going on. Because as soon as it became clear that radiation was this complicated spectrum, and that whether it was stuff in laboratories or in space, like stars, for example, could emit radiation, and therefore we could study its properties and so on. People then said, well, okay, instead of taking some light that shines through a window and shining through a prism, why don't we see what the light of the sun looks like? And it was basically towards the beginning of the scientific study of solar radiation that people perceived what, not just the fact that you could decompose light into different colors, but that there were these seemingly discrete, sudden features in the spectrum of the sun, these black bands here. And it was folks like William Wollaston and Fraunhofer, again, in the early 20th century, who noticed that, hey, these features tend to be omnipresent, whether it's in radiation from the sun or other sources, even terrestrial sources where if you shine a flame or have light from a flame pierce some like gaseous object, you can see these features show up, and we call these spectral lines. Now, again, all of these observations came at a time where those features were not predicted or predictable. People didn't really know or understand what they were being, they were coming from. But it was in that era that other movements within physics began, and it was specifically the understanding of matter at like the particulate level, literally just perceiving matter as particles and all that stuff. That really also didn't arise until the 18th, 19th century in earnest in terms of an actual field that could lead to detailed calculations and so on. And the idea is that it took many experiments done by many peoples over several centuries, whether it's Bunsen of the Bunsen-Burner fame, or Marie Curie of Nobel Prize fame and so on, did these laboratory experiments showing that, oh, matter and light can interact. And there is this fundamental connection between how matter operates at the quantum level, at what we now call the quantum level, and the ways in which they can either receive or emit radiation. That connection took a long time to discern, but it was eventually discerned. And again, in terms of what we can perceive now, the examples I showed in the previous slide are examples of what are called absorption lines. Absorption because presumably there's radiation at those points, but something is absorbing all that intensity out. But not only do we observe absorption lines, but also emission lines. And again, in this 19th, 20th century era, as people were perceiving these features in the spectra of stars, those were basically one of the big primary motivators for what we now basically call quantum mechanics. And arguably one of the big things that drove quantum mechanics as a field was that scientists wanted to understand what were causing these phenomena, basically. And it was through the exploration of how particles behave at that quantum level that people were able to then say, oh, okay, it turns out these specific features are associated with a specific molecule or element. And then people started to explore what other elements could give in terms of potential emission or absorption lines under specific circumstances. So now, again, in terms of just like the very crash course history of the physics, so to speak, of spectral lines, this is where the hydrogen line actually enters, because it was in the era of the end of World War II. Again, there was a lot of natural work done in the radio instrumentation regime for communications, of course, but there was natural synergies with radio instrumentation and radio astronomy and science overall, but there was also movements, again, because of this long-standing problem of spectral lines being this omnipresent phenomenon. Folks over in Europe, specifically Hendrik van der Hulst, was tasked with understanding, hey, okay, at that point it was understood that elements could give lines. Were there other lines that could be predicted in terms of what we understood hydrogen, for example, to be? And so the academic advisor of van der Hulst, who I believe was Jan Wort, actually asked him, hey, could you see if hydrogen, for example, could naturally give out a line? And Hendrik van der Hulst predicted that there indeed would be a spectral line around this frequency owing to the fact that hydrogen fundamentally is the union of a proton and electron, and quantum physics predicts, or at least postulates, that there are several features that define each of those two particles. For example, orientation, what we call spin, indicated by the arrows on the right. And the idea is that there are these natural, albeit highly unlikely, but again, natural occurrences of what's called a spin flip transition, a reorientation of these two particles that are bound together. And it's during that transition that it would be predicted that there would be this loss of energy through radiation. And it's that radiation, as van der Waals predicted, would correspond to an electromagnetic frequency of 1.2 gigahertz. And so, again, this was postulated, or at least theorized, in 1944. But the Europeans, or the folks in the Netherlands, Jan Hort and students and so on, had a really, really hard time, from my understanding, had a very hard time trying to actually observe their predicted feature. And there's actually a very lovely write-up a brief write-up of all of this, I think, in one of the Green Bay websites. But apparently they had a lot of struggles with how to do the proper, what we now call DSP, digital signal processing, to like filter out the noise and extract the signal. But folks over at Harvard, specifically Ed Purcell and a student, Doc Ewan, specifically Doc Ewan, I think, created the filtering techniques necessary to place limits on and extract the expected feature. And it was through their work at Cambridge that they were able to indeed detect for the first time the presence of the hydrogen line at that specific predicted frequency. And here I've shown several photos, all of Doc Ewan, basically with the directional horn antenna that they constructed for their experiment. This is was on the rooftop of, I think, of the still current physics building over at Harvard, which is, fun fact, 20 minutes away from my parents' house. And the middle picture is the receiving technology that they had developed in the laboratory over at Harvard. And then over the years, thankfully, the horn that they had constructed was donated to Green Bay, which is the horn that's on the lawn in front of this building. And oh yeah, like I said, if you go to this, there's a really lovely several-page write-up of just the 20-centimeter line, its brief history, and so on. Very, very neat stuff. So again, this so far has been a crash course in what the hydrogen line is and how it was found. But it turns out that what makes the hydrogen line special, and something that's of focus in radio astronomy in particular, is a several-fold set of circumstances. One, which is probably the most quote-unquote obvious, or at least easiest to understand, is that given the way that radiation basically does not really interact as much with, say, dust or the atmosphere as most other parts of the spectrum do, if there's this naturally occurring phenomenon that we can observe from the Earth, saves lots of money to, instead of having to worry about raising the many hundreds of millions to launch something on a spaceship, we can just create stuff here on Earth and perceive it through the atmosphere. And so that was a huge boon for sure, because again, as this nice graphic from NASA shows you, a vast majority of the spectrum really is not transparent due to the atmosphere. Whereas for radio astronomy, we're very fortunate that we can build lots of ground-based technologies to acquire radiation from the cosmos. And again, one of the primary motivators for understanding if hydrogen could emit radiation was that these features, for example, the atmospheric opacity or the lack thereof at radio frequencies, was known at that time and understood by John Hort and company. But the idea was that, we want to study these things. It's hard to study the optical, which was then the most prominent way of observing stars and distant features out beyond our solar system. But if there was something, a natural source of backlight, so to speak, at radio frequencies, as Jan Hort sort of predicted, we could then come up with much cheaper and clever ways of observing distant parts of our own galaxy. That was Jan Hort's specialty, basically, was studying the Milky Way galaxy. Because of the fact that radio emission just pierces through Earth's atmosphere. So again, one reason it's special is because it's just easier to observe on, and that makes it technologically way more feasible, way more affordable, and so on. Another reason why it's so special, though, is because, again, a known effect at that time, the Doppler shift. The idea here being that because we have these naturally occurring markers, so to speak, in the spectrum, these spectral lines, whether they're emission or absorption, we can set up laboratory experiments to make sense of these lines and associate them with certain chemicals and certain physical processes within those chemicals, which is what that middle colored band shows, the neutral or like rest frame spectrum. We show features at specific frequencies, right? But if the source of that radiation is moving, then due to the Doppler shift, the location of those lines themselves would shift. And so in that sense, it ended up becoming important as a tool for physics and astronomy to try to observe these lines emanating from different sources out, again, in that era, in our galaxy, because we knew the galaxy, or it was postulated that the galaxy was dynamic. And so in that sense, Jan Oort specifically was interested in trying to understand the structure of our Milky Way galaxy. We now know it to be spiral. At the time, it wasn't even understood. And this work essentially led to that understanding, was how do we make sense of, what is our galaxy made up of, how much hydrogen is in it, what's its structure, and so on. And so because of the Doppler shift and these natural discrete features that are spectral lines, the idea is that if there is neutral hydrogen emission in our galaxy, then we can use it to study the dynamics and kinematics of the sources of those radiations in our galaxy. And so in fact, I think it was even barely, it was like 10, 15-ish years after it was 10 plus years after the theoretical discovery of the neutral hydrogen line, but it was only 5 or 7 years after the actual observational discovery of the line. Jan Oort and others redeveloped, the folks in the US, folks in Europe collaborated, and established ways in which they could elucidate these features from their different observing radio telescopes. And Jan Oort and company actually use it to indeed create the first maps of our own Milky Way galaxy, as shown on the right, and even create the first instance of what I'm going to refer to later as a rotation curve, just mapping out how fast things move depending on how far they are from the center of the galaxy. Back in before 1960. So this was very much a quick succession of, okay, here's this theoretical thing. Some years later, it was found observationally out in nature. And once it was found, people then quickly transitioned to try to use it as a tool. And that's a very common theme in physics in general, is once you find something that can have some use as a kind of tool, then people will move to try and exploit those, its utility. So a lot of this came in quick succession in the history of physics. But again, it was during this time, even before Jan Oort and company created the first maps, there was a lot of, once the hydrogen line was discovered, people started to then speculate, which is another common occurrence in physics, as to, okay, now that this feature is known, what can be done with those features, right? What else can we access in terms of new environments, new ways in which we can perceive things around us, whether it's in our solar system, especially outside of it. And it was speculated, again, in the early 20th century, our understanding of what galaxies were evolved pretty quickly with the work of Edwin Hubble. Our understanding of what the universe was in terms of its makeup, its dynamics, and so on, was itself, evolved, especially when Albert Einstein postulated his general theory of relativity. And over time, the nature of matter in the universe and in the history of the universe also rapidly evolved as well. So once it became clear that hydrogen truly was one of the most, if not the most abundant element in the universe, people said, well, okay, hydrogen is super abundant throughout the history of the universe, and we now know that, and have proven that, again, clumps of hydrogen can naturally emit the source of radiation. That means that we can access not only different parts of our galaxy, different parts of the universe, but different times of the universe as well. And this became a really crucial aspect, not just for physics in general, but for radio astronomy especially. And so with that, I'll move on to the applications, because again, once it was understood that the hydrogen line could naturally serve as this tool for the astrophysical sciences, a lot of work basically went into the cultivation and development of radio astronomy. And in fact, the majority of working radio telescopes, and at one point, arguably even all radio telescopes, almost all, were designed so that they could be sensitive to or tuned to the 1.4 gigahertz part of the spectrum because of the presence of the line. Again, there are other famous telescopes, of course, that don't operate at those frequencies, but the vast majority of telescopes, even now, as I'll show in a little bit, still use and design their receivers and digitizing technologies so as to resolve the hydrogen line spectrum. And as you can figure, and as I mentioned already in words, but as I'll show in detail, even modern work that involves a neutral hydrogen line spans many different scales, whether or not you're interested in studying the structure of not just our own galaxy, but other galaxies, the way that matter in the universe is distributed, or bigger picture questions in cosmology, like trying to access the earliest times of the universe, because in astronomy, time is equal to distance. So if you look longer, you look farther, and all that good stuff. And I'll show in a brief slide or two that there's even some connections to the ways in which SETI and other folks and other projects that seek to constrain the presence of extraterrestrial intelligence have actually used and or noted the hydrogen line as a potentially interesting frequency to tune into. So again, as maybe some folks are aware, with modern instruments, whether it's Green Bank, of course, or the Very Large Array and other arrays that are now coming online, you can just access different parts of things that emit at all sorts of in all sorts of regimes of the electromagnetic spectrum. So on the leftmost image here is shown, I believe it's the Southern Pinwheel Galaxy, M83. Yeah. So the leftmost image is that obtained from Hubble telescope, but the middle and the right image show what happens when you instead look at that same thing, or the same galaxy, but with ELA, given its substantial resolving power. And again, given the presence of neutral hydrogen in that galaxy where you get line emission, you can see that there are features that largely overlap, but also there are features that do or do not coincide with optical emission. So you really are accessing really different parts and different phenomena that induce that radiation as well. And so neutral hydrogen in that sense remains this really important feature that folks seek to find in different parts of the universe. And as I had mentioned before, Jan Oort was, I don't know if it was the first, but it was certainly one of the earliest examples of using H1 emission and mapping how that frequency changes due to the Doppler shift, the presumed motion of the source emitting the H1 emission, that allowed for the resolution of what we call rotation curves, which are the velocities of the sources emitting that radiation as a function of distance from the center. And so this was work that, again, had been done initially with optical telescopes, and that's what those yellow points show is with optical light, with light you can perceive with visibly oriented experiments, you can very much, use those images to track how fast things are moving. However, at some point, there ends up being this lack of visible matter as you go farther and farther away from the center of, in this case, I think it's M33, is the galaxy shown here, I think, is shown here from this one. But with radio observations, you actually, again, even if there's no optical emission, and if there's hydrogen in those areas, then you can actually use those to observe different parts of the spectrum, and specifically the hydrogen line, which is what the blue observations are, and which crucially allows for the resolution of rates of change of matter about the centers of their galaxies at much farther distances. And one of the reasons this was crucial, as briefly noted in the bottom, is that this allowed for the resolution of a very key discrepancy with what was predicted or expected from purely Keplerian motion, Keplerian motion being orbital motion, the Earth going around the sun, the moon going around Earth, and so on. When you apply that theoretical framework to galaxies, you would expect to see what is that dashed curve, where there's more matter towards the center, and so the velocities are higher when you're closer in, but then as you go farther away, there's less matter, presumably less matter outside of you, and because of that, that dictates how fast you move, and so you would expect this decreasing in the frequency as you go farther away. And again, that's if if all matter is associated with the visible stuff, right? However, your Rubin and company saw, no, actually, we see this persistent flattening of the rotation curve that they argued was lent credence to the existence of what we now call dark. So this was a really key observation that they had made, and they didn't only make it with neutral hydrogen emission, but neutral hydrogen really very much was and remains one of the key tools for gauging these sorts of phenomena. And again, it comes directly from this simple emission of a spectral line due to hydrogen. Now, one of the major things that's been going on for the last 10 plus years or so is the development of a technique called line intensity mapping. Now, as the name suggests, it's basically the construction of instruments, telescopes, experiments that focus on trying to collect as much as possible measurements of radiation from all over the sky, but specifically that associated with the emission of spectral lines. Now, as I'll show in a schematic in a second, hydrogen is not the only element, of course, that emits spectral lines. And in fact, I don't know how many folks who are into the astrophysical science look at the archives, like this public repository for papers and all that kind of stuff. I looked at it this morning, and like half the papers center on the analysis of spectral lines, whether it's the hydrogen line, carbon, oxygen, hydroxyl, all that kind of stuff. There's all sorts of different compounds and elements that can give off line features. Hydrogen though, as I mentioned already, and as I'll re-emphasize, because it's the most abundant, that means that it basically will allow you to acquire radiation from naively and presumably the earliest times of the universe, or as far back as possible. And so because of that prospect, folks have worked towards creating the means necessary to generate these large-scale surveys of line emission. And because the emission of lines associated with what we call baryonic matter like hydrogen, etc., because we know it's copious and abundant, therefore we ought to be able to acquire the radiation even if we cannot resolve the source itself. And so on the left here, I believe, are simulations of like clumps of galaxies, and this kind of a slice of what's called large-scale structure. But the idea is that those individual galaxies will contain stars, star-forming regions, places where there's clumps of hydrogen where this light emission would come from. And even if the telescopes cannot resolve those individual stars and galaxies, of course, the emission of neutral hydrogen, because of just how abundant it is, would nonetheless allow for these, fuzzy kind of, nonetheless non-zero regions of total intensity associated with the hydrogen line. And in that sense, you can create these, again, fuzzy, albeit significant maps of hydrogen emission across a large range of distances in time. And it's through the presence of that line emission that folks then seek to basically understand how matter is distributed in the early universe, or in different parts and times of the universe. And so line intensity mapping is very much a core motivator of a lot of ongoing radio astronomy experiments, specifically for cosmology, because like I said in words a moment ago, there are all sorts of chemical elements and compounds that produce line emission. And so the shorter line below the 21 centimeter line, that shows basically, given our understanding of how elements in the universe form over time, there ought to be all sorts of what we typically call metals, but just like elements heavier than hydrogen, we call metals basically. And the presence of those elements are basically understood to have occurred pretty early on in the history of the universe, but there's still this huge range of time where it was basically just mainly hydrogen and some helium, right? But again, it's because of the fact that hydrogen is so abundant that in principle, with the right telescopes and the right technology, we can go as far back as possible. Again, you just need the appropriate techniques, and especially for line intensity mapping, calibration of the instrument is super important, and it makes it very, very challenging. But in principle, so long as those systematics can be worked out, we could, in theory, receive radiation from the 21 centimeter line throughout the majority of the history of the universe. And that's why it's such a crucial focus. Now, here are some examples of radio telescopes and experiments that I think are all funded and almost near totally built, that are, again, not only but primarily driven by resolving and imaging the radio sky, specifically at the frequencies corresponding to neutral hydrogen, well, specifically to image the neutral hydrogen line from sources that are at much earlier times in the universe, but again, because of the expansion of the universe, there will be redshifted, and so in that sense, they're tuned to frequencies where they ought to be able to perceive the redshifted 21 centimeter one. As Marcus noted earlier, myself and a colleague of mine, Adam Dong, who's sitting over there, we helped build the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. We did so over the past decade or so. But there are other experiments located at various parts of the world, with all funny acronyms and so on, that, again, all have a similar purpose of trying to make these large-scale maps of the universe, but specifically of the 21 centimeter emission at different cosmological redshifts or times where the expansion rate was at a specific rate. So again, in the absence of any other information, 21 centimeters as an effect that radio astronomers like to tune into really remains a core component of radio astronomical research. Now, like Marcus also mentioned, I'm a pulsar astronomer, so it's not something I typically engage with from the research side, but again, we naturally prominently teach all about it because of just how omnipresent it is and how crucial it's been for the development of our understanding about how nature works and how the universe operates on various scales. But like I mentioned before, when I was doing some research to understand what role does the neutral hydrogen line play? There's also a really interesting history with, or connection between the hydrogen line and the Search for Extraterrestrial Intelligence, or SETI, where again, fundamentally, I'm sure folks know it here. SETI seeks to find artificial signals, presumably emitted by super intelligent species, who, naturally would try to emit at radio frequencies due to its transparent nature and low cost nature as well. But it was pretty early on, like shortly after the experimental verification of the existence of the neutral hydrogen line, that folks, like these folks I know over here, argued in the Nature magazine that, hey, SETI being this thing that people have thought about for a long time, it turns out that because of this connection between the emission of radiation by this most abundant element in our galaxy and certainly the universe, it's likely that a super intelligent species would try to tap into that, maybe mimic that, or utilize that feature so that less intelligent species like ourselves may, want to look and make sense of those features, and maybe that through that channel, so to speak, we can establish content. Again, obviously very hypothetical, nonetheless very neat. And so there's been gradually some work done to develop concepts, again, based on pretty strong hypotheses, but nonetheless develop concepts of trying to utilize or exploit the existence of the hydrogen line to then see if there are folks who are tuning into or emitting at those frequencies and so on. And again, it's not a field I'm super familiar with, but nonetheless very interesting in terms of what role it has played even on those fronts. And again, for folks who like to tune into a little bit of interesting, fun history, certainly folks have seen this final record, well, not final, but folks have seen this record before. It's the golden record currently on Voyager. From my understanding, both on the Voyager golden record and even the Pioneer plaques as well, I think, there are etchings and or the acknowledgements of the hydrogen line on these things, because again, it is a natural, ubiquitous phenomenon that if we were able to perceive, others out there could. And so the acknowledgement of the fundamental physical process, the spin flip, so to speak, which is what's kind of very vaguely, albeit directly shown there. It was noted there so that we could tell some species in the distance, hey, we're not that dumb. We understood this and we acknowledged it too. And fun fact, these lines, for folks who don't know, these seemingly random lines actually denote the location of the solar system relative to a bunch of radio pulsars. So that's always a fun fact I like to point out too. All right, so just to end, I'm not sure how late or not I am, but just to end, again, the neutral hydrogen line truly is and remains one of the most important scientific tools made available to astronomers today. It is something that has allowed us to make sense of our own galaxy, establish its final nature, seek out all sorts of really interesting regions, whether in our galaxy or outside of it, where stars form, and it's through that synthesis of whether you're interested in learning how the elements form through the fusion in stars, or if you just want a bigger picture thing and try to gauge the presence of dark matter and or even dark energy, which is what folks do with light intensity mapping experiments, all of that is centered on using the hydrogen line. But again, as I mentioned towards the beginning, the hydrogen line itself has a really interesting history in terms of its connection to the establishment of quantum mechanics as one of the modern fields of physics, and just the ways in which people sought to understand what these things are that we can perceive through all sorts of really interesting experiments. So whether you're interested in our own galaxy, the universe at large, or even interstellar telecommunications, the hydrogen line has a really interesting role to play in all of those things. So with that, I'll end, but thank you for your time. Really appreciate it.
Certainly time for questions, so we're right on time, so excellent, and I really appreciate the talk. I want to make an out loud apology, because when we first talked with Dr. Fonseca, he said, so what's the topic? I was like, oh, I said, well, I'll tell you what, we've got the scope in the box. I know hydrogen has been a big topic of us. How about the hydrogen line? And he was sounds good. And so it was a couple of weeks ago, whenever I was writing his bio together, I was like, his specialty is fast radio bursts and pulsars. So he's a true champion. He let me take him off of his research topic and went down this path. So I appreciate it very much. Certainly time for questions. We'll start inside here first, inside the room. So questions, Skip?
Is it I'm just a question, is it well known that if you could bring up the golden record again?
Yeah.
Is it well known that there's an error up there near the top? on the measurement of the spacing between the two pulses?
Is it,
Well, it turns out a friend of mine, or a guy who used to work for me, yesterday, he discovered that the pulse duration in engineering, we usually start from the start of the pulse to the start of the pulse. That goes from the start to the end. And he was working on a project to produce a golden record digitally by imaging one of the original models that was used to encode the data. It was a very big project. But he discovered that problem and he realized that that would mean that the circle that was encoded would not come out to be a circle, it would be an oval. So I talked to Frank Drake about this here in Green Bay. And I asked him about that. The line makes the dimensions incorrect in encoding. Everything can still be decoded because they'll see an oval instead of a circle. And I asked Frank Drake about it. He said, he concluded, well, yeah, it's one of those things. Either humans make mistakes or they want to tell them that we make mistakes.
well, right, yeah. No, but also, I mean, so from my understanding, and you can correct me if I'm wrong, from my understanding, at least for the, no, I think also on the Pioneer class, like the space, it's hard to resolve on this slide, but there's etchings along each of these lines that connects the solar system to a pulsar. There's etchings that are meant to denote the period of the pulsar as it spins. But apparently the folks who created the record chose to denote the spacings to be in units relative to 2170 or 1.4 gigahertz. And it's the same with, from my understanding, the height of the woman
Yes.
portrayed in the Pioneer flag is like 8 times 2170.
Yeah.
So like it was chosen to like reflect, again, this is the whole like, hey, we're smart, you know, like we're trying to communicate that like, oh, this number is special and here's why, you know.
Yeah, Rick
I think.
Rick wanted to create the actual sounds that someone else would see when they got the record.
Sure.
But he didn't want to use the original tape recordings. And so he had to he wanted to recreate the whole thing when it happened. Yeah.
Well, so I got on radio astronomy like 4 days ago, so I'm very new to this. So thank you for being here. That's really interesting. What is, for say, radio pulsars when you study fast burst radio pulsars?
I study 2 kinds of phenomena. One is radio pulsars, which are, have you heard of neutron stars?
Mm-hmm.
Yeah, so neutron stars are as, in my mind, they're as close as what you can get, they're as closest to black holes as you can get without turning into a black hole, basically. But in my mind, they represent the most extreme physical environments that we can make sense of because of the fact that these pulsars emit pulses for all sorts of reasons. Fast radio bursts are, they look like pulsars in terms of how they behave with the intervening environments. They're like these singular flashes of radiation, but they come from sources that we believe to be mostly neutron stars, but they may not be. Like, they're more mysterious, but they're also a cosmological population. Fast radio bursts are almost definitionally extragalactic. So we observe them coming from high cosmological redshifts, from all sorts of different galaxies and so on. So that's what I've heard these on.
Okay, thank you. I was just curious, so like we use the hydrogen line to, you know, you can kind of make a structure of the galaxy. For what you study, can you use that as a tool to do any science?
So for what I study, can I use, maybe not the
structure.
line, but
Sorry, yeah, I phrased that weirdly. Like we use the hydrogen line as a tool to study like the structure of the galaxy.
yeah.
Can you use what you study as a tool to like study something else?
Yeah, no, absolutely. That's a great question. In fact, I was talking with Tom earlier because so pulsars, they were discovered by Jocelyn Bell Burnell in the late 60s. I think it was the year after Sgt. Pepper's came out. Like within a few years after the first pulsar was found by Jocelyn and her advisor, people started to, they established that pulsars, they essentially act like clocks, like the adjacent pulsars are kind of come at super regular intervals that rival the ticking of a clock, basically. And so because of that, when you hear pulsars, think of clocks, and for physicists, clocks and meter sticks are among the most important tools they use to make all sorts of measurements. And so when I was chatting with Tom earlier, I remembered that one of the most prominent figures in my field, his name is Joe Taylor. From my understanding, he's a very prominent ham radio operator.
Former speaker.
Former speaker. Okay. And from my understanding, his call sign is WT2. JT. Oh, sure, JT.
Joe Taylor.
Yeah, of
JT.
course. So he used a pulsar in a binary system, so a pulsar orbiting another star, to eventually, over a 7 to 10 year period, to show that the orbit was shrinking at a rate that was almost exactly consistent with the emission of gravitational waves. And at that point, gravitational waves were one of the last major predictions of Einstein's theory. I mean, the prediction goes back to like the 20s or 30s, I think. But Joe Taylor and his student Russ Holz made that discovery in early 70s, I think. And they won the Nobel Prize for it, because it basically, a lot of modern day gravitational wave physicists say, oh, they indirectly discovered it. But and it's true, they weren't observing the actual gravitational waves, they were observing the effect that the release of gravitational waves was having on the binary system, which causing it to shrink, because waves carry energy and all that kind of stuff. But Joe used a pulsar in a binary system to observe that rate of change, or orbital decay, as we call it, that exactly matched the prediction of the existence of gravitational waves. And it essentially motivated the existence of LIGO, the Laser Interferometer Gravitational Wave Experiment. Like, I think once the NSF saw these things do exist, then they're like, hey guys, here's billions of dollars, go build your instrument. But with pulsars, you can study them very cheap. So we use them for tools like that all the time.
So, room, any other questions? Good.
When you're talking about the spin of the electron, at a quantum level, is spin like the electron spinning like we think of?
No, it's a good question. I mean, no. It's like, yeah, the concept of spin when studying quantum mechanics is very tricky, because like you said, at the quantum level, like those particles are not meant to necessarily have like they're not meant to be treated like the classical mechanics of like extended bodies like the Earth or the Sun, you know. So the spin is more associated with the fact that the particles are charged and they interact with magnetic fields as well. So the spin is usually associated with like magnetic dipole orientation, all that kind of stuff. So it's very much it's a good question and a tricky one to answer. But it has to do with the ways in which each of those two particles, the proton and electron themselves, have electromagnetic properties, and the spin's meant to help sort of describe the ways in which they interact with electromagnetic.
Kind of like a random label that goes on it, like, oh, it's a red quark.
Right, yeah.
No.
Yeah, right, yeah.
Jim, did you have a question or comment?
I have a question about what do you think the possibilities are of somebody with small telescopes being able to detect the fast radio bursts? What Jansky level are you talking about, or what?
That's a really good question, because this was arguably shown not that long, like, so these folks over at Caltech, California Institute of Technology, they built this like dirt cheap telescope called SARA 2. It's some acronym. But I mean, do you remember, Adam, what it was made up of? Like, what was the instrument that it was like? I remember hearing that it was like a bunch of cut in half soda cans that had like little tiny receivers in them, but I'm sure it's not quite that. But it's like this really small scale cheap thing. But nonetheless, they put little receivers in them that were tuned to like L-band or something. Is that right? Yeah, L-band. Right, and so they again
supporting the H1 line. L-band is H1.
Right. Yeah. There you go. And again, very cheap, very much like, and because of its lack of, you know, focusing antenna, all that, focusing mesh, all that kind of stuff. It basically was a small sky monitor. It was a receiver pointed straight up, and it was very much a like low risk, high reward. Low risk because it was very cheap, but high reward they could see something associated with an astrophysical event. But nonetheless, like, you know, and sure enough, in 2020, they, along with CHIME, which was a much more expensive, much more sophisticated radio telescope, simultaneously detected this galactic source, what's called a magneton. It's a highly magnified neutron star, emit a burst that essentially, if it was placed in Andromeda, we would have said, oh, it's a fast radio burst. But it was so bright that in terms of physical units, it was like, do you remember the unit? Was it megajanskis?
It was something on the order of 10 megajanskis. You'll see it. You'll see it with like the smallest telescope.
Yeah, so long story short, yes, absolutely.
But you need to point at the right place. So I would say point all your little radio telescopes at magnetars that could give up these fast radio bursts.
Right.
And then it'll be a nature publication.
And there are folks now, for example, there are folks, I believe in South Korea, who are actually building these sort of, again, dipole antennas, dipole telescopes that are just antennas pointing straight up. So they have like unbiased coverage of the sky, basically. They can't really localize or pinpoint very well, but they ought to be able to detect stuff like this, like many times per day or something.
The Taiwanese first
Taiwan.
project is many little telescopes spread out throughout the world. I think one on Hawaii, one in Taiwan, and all that. But they're very small telescopes, so they don't have much sensitivity. But because they're spread out, they
Yeah, because of the lack of sensitivity, in reality, they're only gonna find these sorts of like local sources, but like, again, the discovery of that first like mega Janssen burst was not quite the wow signal, because from my understanding, the wow signal was like many seconds or something that long, whereas the thing that was seen in 2020 was like, again, milliseconds, very brief, but yeah, they can get that under jet.
So maybe a SARA project, Jim, you could write up for all of our amateurs to.
Well, luck is your best ally in
There you
this.
No, but I'll happily share it, I think not
Do
that
you
long.
have a paper source for that?
Well, I was just about to say, not long ago, these folks, originally from Caltech, I think the guy is now a professor at Harvard, they put out a paper of this, a similar experiment called G-Rex, which is essentially like a radio telescope with a suitcase, but it has a similar structure that's meant to be.
And you don't need federal funding for it.
No, and in fact, they were trying to sell it as like this really dirt cheap, simple project, basically. It may not be several thousand, but it's not quite, like major instrumentation, for sure. But it's all about like what sort of stuff you want to study, and again, for some folks, they're really interested in understanding the nearest by, highly magnetized environments where, again, at those frequencies, you get Faraday rotation, you get all these really interesting physical effects that can be perceived quite readily.
Yes, kid.
Is it possible to get time on this CHIME, like, you worked on CHIME, a copy?
Yeah, the one over here.
Cylindrical dish.
Did you folks, was there a tour to that at all? Like, because there is that's right, Skip reminded me, there is like a small scale copy of CHIME here that's actually meant to work in tandem with the main CHIME to enable very long baseline interferometry. So it's not yet like an open source or it's not yet like an open sky resource. I mean, I remember I was chatting with the previous director, Jim Jackson, because he was really interested in trying to have there be like a partnership between Green Bank Telescope and CHIME. So if folks submit a Green Bank Telescope, they can also request time on the CHIME telescope for the same project. And I think it's our intent to eventually do that in the next several years. I mean, CHIME, it's very much like, I tend to think of CHIME as a grassroots effort. Like there's technically one operator, but there's 50 or so students and faculty and postdocs, and we all collectively serve as the maintainers of the instrument. I mean, I can tell you, 2 hours of my day are spent system administrating computers that are seemingly on fire and stuff like that. I mean, it's worth it, but it's, there's a lot, it's, in that sense, we're almost, but not quite at the point where it's like, oh, it's like plug and play, easy to use, but we're getting, and there's definitely an openness for data to be more easily accessible.
So I just put the FRB database from CHIME on my little astronomy viewing program, radio astronomy program. And it doesn't include a lot of recent observations. So how quickly do they come out? When it's detected to when somebody could use that information to compare with their own?
Yeah, that's a great question. So it's likely not as obvious because it's more of a service tuned into. It's not, I mean, anyone can tap into it, but it's definitely most transparent to researchers. But there is a service, it's called the VO event service. It's essentially a near real time, basically to answer your question, when an FRB is detected, within several minutes, there's an alert sent out to folks who subscribe to this broadcast to know, oh, hey, an FRB was detected by CHIME a few minutes ago. Here are its like rough parameters, like where was it in the sky, how bright was it, etc. So it's not on like the main website. The main website is meant to host like the more long-term things, like when we publish papers or we publish data sets that we publish through papers. But there are services in place to notify the public of the real time. Yeah.
And is that like a free service that
Yeah.
anybody could?
Yeah.
So it's just a server that pumps that out and you just connect to it?
That's right. Yeah. There's one of the servers we have. Is dedicated to hosting the showcase. Yeah. Yeah, so I mean, I'm happy to pass that information along too, because there are folks who, because, I mean, especially with stuff like that, the transient sciences, and I believe there's gonna be a talk tomorrow on radio transients. There's a lot of benefit in folks with different telescopes to try and follow up, like when a gamma ray bursts, a telescope finds something. Folks can point, in fact, like when LIGO made their gravitational detection of the source in 2017, the VLA, GBT, everyone pointed their telescopes at all parts of the spectrum to the source, and they found this, the remnants of a kilonova basically. It was a huge deal because it confirmed all sorts of theories about how matter is formed in those environments. So the service is created to enable the sorts of multi-wavelength, multi-messenger flight. And it's
I have an online question. Am I coming through?
yeah.
Oh, great, fantastic. Since it was mentioned that you worked on the nanograv project, and I'm curious, was there any directionality that was observed from any of those results? I know it wasn't exactly clear what the exact gravitational waves were that were detected. I'm just curious if there was any particular orientation that had a stronger strength of gravitational interactions, or was it just purely isotropic?
Yeah, no, that's a great question. So far it is consistent with an isotropic background. So for folks who aren't familiar, nanograv uses pulsars that are largely observed with Green Bank to use each pulsar as like a detector, basically. And the idea is that when you have all these detectors located in different places and stuff, if you can find a correlated signature in those data, that ought to be basically just given the way that we understand physics to behave, either locally here on Earth or elsewhere, the correlated signature among all those detectors ought to be a gravitational wave. And so, nanograv was one of several teams around the world that coordinated to publish their findings that there is indeed significant evidence for a correlated signature in these nanograv or pulsar timing array, as we call it, data that's consistent with a stochastic background of gravitational waves being emitted by supermassive black holes that are inspiraling towards each other. They haven't yet found any evidence for preferred direction, although that's actually the next frontier. There are folks, for example, there's some folks at West Virginia University where I work who intentionally and actively study nearby galaxy clusters like Fornax and all these other ones that have special names, because they're essentially believed to be among the first local sources of gravitational waves to be found, because they're the closest to us. And so, but the idea is that given the nature of how nanograv and other experiments like it are sensitive to gravitational waves, it was always understood that the very first thing would be most likely be the stochastic background, as we call it. And then within the next, hopefully, decade, the first what we call continuous wave, but in reality is like local resolvable sources of gravitational waves ought to be resolved soon as well. So not yet directional, but it's understood that at some point, there's even actually tentative evidence for discrete features in that part of the gravitational wave spectrum that likely arises from a specific nearby source. But it's still like, in the language of statistics, it's like 3 sigma, so not quite significant. But with 5 to 10 years more data, if it goes beyond 5, if it becomes unambiguously significant, then it's the flag that says, we found something here.
So were there any particular gravitational wavelengths that were detected, or were these just a kind of a noise of multiple wavelengths of gravitational waves?
Yeah, so for the isotropic stochastic background, it's within some specific part of the nanohertz spectrum. So it goes even into the sub-nanohertz spectrum on some level. But that nebulous, potentially discrete feature, that was around 4 nanohertz. So there are, again, the dominant significant result that spanned an order of magnitude around the nanohertz regime. But again, there is vague evidence for a discrete feature somewhere in the nanohertz spectrum.
Great, thank you very much.
Thank you. There was a hand raised back there?
Yeah, it was kind of like a follow-up, because the directionality, is it in your data, you see the change in pulsar arrival is greater to the pulsars closer to the event that causes the gravitational wave? It's because you're using that as your network, that as your array.
Yeah.
And so is that the reasoning you're gonna
Yeah, no,
Sorry, the question is forming in my mind as a.
no, I understand, it's a good question. It's kind of tricky to answer because as with electromagnetic radiation, gravitational radiation is understood to have polarizations to it,
Right,
for sure, so, so if you assume general relativity is correct, which is sort of passive part so far. Depending on, like you said, where the pulsars we use are located, we're gonna see the stretching and squeezing of space-time, so to speak, in certain directions relative to where the source is and relative to where you're detecting elements are. So there's definitely an interplay there, and in fact, when you go into the nanograph literature, the phrase you'll often hear is the Hellings and Downs curve. That's the actual figure people tend to make of the signal strength as a function of how angularly separated the pulsars are in the array. Because like you said, or what you're getting at, is that it does actually matter where these things are placed.
right,
Like there's a relative strength increase or decrease depending on how far apart these things are.
right,
So it's not the most straightforward, like, yeah, if you're observing pulsars in the same direction as the thing emitting gravitational wave, you're gonna get the largest amount of strength, so to speak. But because of the polarization of gravitational waves, even if you observe a pulsar 90 degrees away, you'll still see something. It'll just be somewhat faint, and you'll see something if it's 180 from you, but it'll be in the opposite direction. So there's a funny interplay owing to the polarization of it.
yeah, cool, thanks.
Yeah, it's a good question.
Again, thank you very much.